All right, now we can conserve also the third best paper candidate of this session. The paper is titled RF-AcSense or ACSense, device-free activity localization and recognition via passive RFID tag array. And the presenter is Shaoyi Zhu. Please welcome our speaker.
Dear everyone, first I'm very honored to stand here and introduce the main work of my paper, RF-AcSense device-free activity localization and recognition via passive RFID tag array for you. And I will start my presentation from the following aspects. First is the introduction and the related work. Recently, the popularity of ubiquitous applications such as smart home, remote healthcare, and motion sensing games has made the intelligent sensing technology a hot topic, the foundation of which is a device-free passive human localization and activity recognition. The existing solutions can be roughly divided into the following two categories, according to the necessity of wearing additional devices. First are the device-based approaches. In this kind of methods, additional devices such as smartphone, Bluetooth beacon, RFID tag need to be carried on the body to complete real-time monitoring. Considering the inherent defects of the device-based methods, more researchers began to seek solutions in a non-intrusive way. Thus, the device-free approaches came into being. For example, WIDER and WIDER2 were proposed for passive human tracking, which achieves decimeter-level localization. Gesture recognition was also studied using machine learning, deep learning, or radio image-based methods. And the contribution of our work are listed as follows. First, we design a new device-free solution for simultaneous localization and activity recognition based on RFID. Second, we proposed the upper-lower layer combined localization method and the upper-lower link separate activity recognition mechanism. Third, we implement a proof of concept prototype of the system with costs of RFID devices in real-life environment. And the experiments show that our system can achieve an average localization error of less than 0.22 meters and an average activity recognition accuracy of 94.6%, respectively. Then let's focus on some preliminaries of our work before we get into the main part. As shown in the figure, an array of the RFID tags is passed onto the wall with a two-layer antennas array placed relatively to it. Thus, an RFID-equipped smart space is created with multiple antenna and tag links. Suppose there are P antennas with Q tags communicate normally with each other. Then L links can be formed. The RSSI measurements RM in the mth round will be generated as follows. When the background is static, the RSSI measurement is recorded as R0. The difference delta RM between RM and R0 is used for the next step. Since the Bragg effect of human on the link is so evident and can be used for human state perception, which inspired us to find a new solution for activity localization and recognition based on the RTI framework. There are two main components contained in the RTI, which is weight matrix calculation and image reconstruction. In response to the different needs for localization and activity recognition, the ground plane and the tag array plane are first divided into pixels of the same size, and the weight matrix are calculated respectively, which are shown in the above two figures. Then two radio images can be calculated by the operation between the real-time signal vector and the weight matrix. which can be used to identify the location and activity of the human from the image features. Now let me introduce the general composition and framework of the system to you. The overall architecture of the proposed system is shown in the above figure, which mainly contains the following two parts. The first is the localization module, combines the images of upper and lower layers to finalize the position results. And the tag filtering is added to get the simplified image of the tag plane. For identifying the behavior category, the activity recognition module first adopts the foreground detection method to assist in determining the human's height. Then we divide the simplified image into two parts corresponding to the upper and lower limbs. The 3D convolution-based deep learning network is trained to identify the motions of two parts. Finally, when forming the whole body activity recognition result, the pooling operation can improve recognition accuracy while reducing the computational overhead. In localization module, upper-lower combined localization is performed to achieve the real-time location of the human, specifically giving two layers of antenna as AU and AL. The corresponding tag lines can be expressed as TU and TL. The first step is to capture two subsets of delta IM, representing the differences between the real-time and the background signals of the upper and the lower links. Then combine the weight matrix WG, the image of upper layer IGMU and the image of lower layer IGML can be calculated. To integrate the results of upper and lower layers, the pixel values of the two images are added as IGM. Then we select the pixels with the first n maximum values, and the final location of the human can be calculated as follows. The figure shows the radio image of a human physically located at 0.6 and 1.2. Obviously, the occlusion of human is reflected on the pixels around the specific links with brighter and warmer color. As shown in figure 4A and 4B, when the coordinates of the brightest pixel in the image are regarded as the location of human, the localization error of the upper link and the lower link are 0.158 meters and 0.112 meters. The positioning accuracy is further improved with localization error of 0.05 meters when the results of two layers are combined in a way of superimposed weighted average, which is shown in the figure 4C. Observing that the positioning results obtained by our method are quite accurate, we consider filtering the tag array to extract a valid tag set based on human's location, which can reduce the noise caused by useless tags on the one hand and accelerate the processing speed of the system on the other. So we use the principles such as projection and the triangle similarity to get the coordinate of the valid subset of text TD. And the links generated between TD and the antennas are considered to be capable of discriminating humans' behavior. In stage 2, activity recognition, noted that sitting or standing is the most basic element of an action. It is necessary to first perform height judgment to guide the division of sub-images, which is achieved by comparing the pixel differences between the upper and the lower parts of the image. The height state of the human can be determined by judging whether the differ V exceeds the threshold. As shown in the figure, 8 activities with overlapping upper or lower limb movements are adopted to demonstrate our work. Each of them can be combined from the detailed motions in the upper and the lower categories. And we incorporate sit and stand into still and finally form 5 classes for training as still, bow, wave, swing, and walk. Then we design a 3D convolution-based deep network to extract the features across frames to identify the detailed motions of the upper and lower limbs. The architecture of the network is shown in the figure. The probability distribution over 5 classes can be obtained from the outputs of the hidden layer, which is a basic for subsequent inference of whole body activity. Considering that only one unified classification model common to upper and lower limbs is trained during the classification, the decision tree-based schema is suitable for obtaining the category of the overall activity. At the first level, we discriminate whether the current state of human is sitting or standing. If standing, the sample is further classified by checking the identification result of the lower limb is in place or moving. At last, the class with the highest probability and belongs to the correct upper or lower category is the final result. And the combination of the two parts is the overall activity. Now let me show the performance of the proposed method. We implement a prototype of the system based on cost RFID devices. In order to validate the proposed system on both activity localization and recognition, we recruit 8 volunteers and select 12 corners as the reference positions for data collecting. First, let's check the overall localization performance. The localization errors of 12 reference positions are all less than 0.26 meters, and the total average localization error is 0.186 meters. As for the necessity of using hybrid localization mechanism, it can be seen from the right figure that when using only the upper or lower entertainers, the average localization errors are 0.233 meters and 0.192 meters. While the average localization error has dropped to 0.185 meters when the 2 layers are superimposed to take effect, which indicates the effectiveness of our mechanism. For the accuracy with regard to activity diversity, it can be seen from the figure in the left that for each activity in sit or stand categories, the localization results over different people and positions are joined. It can be concluded that our system is robust to activity diversity and can achieve the average localization error of less than 0.2 meters. As for the accuracy with regard to human diversity, the overall localization accuracy for the 8 volunteers maintains in a high level, which means the system can accurately locate the activity with human diversity. Next, we evaluate the accuracy of RF-AcSense on activity recognition with our detached mechanism and the deep learning network. The confusion matrix presents the detailed results of the upper and lower limbs of each activity. It can be concluded that our system can achieve desirable activity recognition accuracy. To prove that the upper-lower limb separated pattern is better than using whole body data for activity recognition, the additional experiment is conducted using the designed deep network to train and classify 8 whole body activities. And the comparison result between the 2 schema is shown in the right figure, which shows that the detached mode is more stable. We also compare RF-AcSense with the 3 mainstream activity or gesture recognition frameworks. Since all the comparison methods do not distinguish between upper and lower limbs, resulting in poor classification performance of certain categories. The effort of human diversity on the activity recognition performance is shown in right figure. It can be found that our system achieved around 90% accuracy for most of the users. Now let me conclude the whole paper. In this paper, we present the design and the evaluation of RF-AcSense, a passive RFID-based activity recognition and recognition system. First, a smart space with intelligent awareness formed by multiple antenna and tag links was first created. Second, RF-AcSense achieves accurate localization through the upper-lower layer combined mechanism. Third, upper-lower link separated recognition combined with a 3D convolution-based deep learning network is designed to classify the activities. And the RF-AcSense achieves the average localization error of 0.185 meters and average recognition accuracy of 94.6%. Although we have achieved the promising results, there still remain some limitations that we need to work on in the near future. First, we need to improve our system with more activities and a great number of tests. Also, it would be interesting to address the problem of multi-person localization and activity recognition. And that's all. Thank you for listening.
And for questions, where do we have questions? There we have questions.
Great. Thanks for the talk. I have first a quick one. How about regulation? I read that you use an impinge reader in the 800 megahertz. How often are you reading, and is this complying to regulations like dwell time regulations in this band?
Sorry,
So you're using an RFID reader in the 800 megahertz frequency band. I read it in the paper, right?
Yeah.
In this band, there's a regulation. You aren't allowed to use the bandwidth all the time. And are you continuously scanning? Because I think this isn't allowed due to regulations in many countries, because on this band you have a limit. Have you considered this?
Maybe you are mentioned about the noise, the processing method. We interpret and deprecate the data first, and then go to the main part.
Okay, another question maybe. So you have done machine learning, right? What kind of fraction of your data did you use for training, and what kind of data did you use for iteration? Did you split it up?
Oh, okay. In the data collection, we recruit 8 volunteers, and let me back to the because we have work activities like and sit activity and stand activities. So for the 2 work activities, the volunteers can work freely for 30 minutes in the range. And for the sit or stand activities, they are asked to repeatedly perform the 6 specific activities at the 12 positions, and each for 1 minute. And when training, we will use we will separate the training data and the testing data from the whole data set.
Yeah, but how did you separate?
Yeah.
How did you separate it? Did you separate it by user or by time? So did you train with half of the users and then evaluate with the other half of the users, or did you just take a fraction of time of all users and then evaluate with the same users? So is it possible to learn with a set of users and then detect activities from another set of users?
In our method, we just separate the data in all the users, and for all the data we collect, and we separated it.
Thank you.
I think that was the answer. All users were used.
They used all
This is
users.
my understanding.
Yeah, maybe.
Okay. More questions? Yes, we have a question here.
Thanks for the presentation. I believe you're aware that Wi-Fi channel state information can also be used for such activity recognition. Like, how do you compare your method with Wi-Fi based activity recognition? Because for me, Wi-Fi infrastructure is already readily available. For your case, you need to build your infrastructure.
Yes. First, I want to say is different approaches may have their own advantages or disadvantages. For the Wi-Fi approaches, there have some approaches use like a CSI parameters. Yeah. But first is when we need to get this CSI, we maybe need to change the NIC, like the hardware or something. And the second problem is maybe in some privacy situations surroundings, maybe like camera-based method or the Wi-Fi cannot be used in this kind of situations. So maybe RFID can be used in these surroundings or situations.
All right. Last and final question. Quick one.
All right. So do you have a quick comparison between the RFIDs and the camera-based approach for the same application?
You mean the comparison?
Yes. Do you have any thoughts or comparison? And many motion tracking and capture organizations are using smart device camera nowadays. And we have any quick talk you could share with us about it?
Yes. In our experiments, we do not use the camera based or we mainly focus on the wireless signals. Because the camera-based approaches, first, I just said, is a privacy issue, and second, maybe is affected by the light or the surrounding. So we just focus on the RFID signals. And in the experiments, we just focus on the wireless-based approaches.
All right. So let's thank the speaker again.
Thank you.